Okay. Today I will start with the basic properties of algebraic varieties. There is one thing which everybody typically assumes about variety, namely reducibility. Consider the following example. You have a variety x, y equals 0. This is just one equation. It's a variety in C2. Algebraic set in C2. It has 0 divisors. The ring, the corresponding ring, is polynomials. Quotient by x, y equals 0. So it has x and y are 0 divisors. And moreover, the corresponding set is just a cross. You have two lines inside C2, and this is a union of these two lines. These two lines are called irreducible components. Typically, we don't want to have varieties which have this kind of 0 divisors, which have this non-trivial, which can be decomposed, because you can always decompose the variety in its components and work with the components. This is why people start with this irreducible decomposition. Okay, so now I would go to the definition. It was just a motivation, an example of something which is not irreducible. Now the definition of algebraic affine variety is called reducible if it's a union of two smaller affine varieties, like that, like this cross. Or you can consider, for example, something like x squared without y, which is parabola, times x is equal to 0. Then this corresponding variety will have this form. Again, it has two components. Or you can do some other things. There are lots of possibilities for creating this kind of situation. So definition, affine variety is called reducible. So let's, if A is a union of A1 with A2, where A1, A2 are varieties as well. And moreover, A of 1 doesn't contain A2, A2 doesn't contain A1. So this is a true decomposition and not something artificial. This is a geometric characterization of irreducible, well, reducible, irreducible. A is irreducible. Irreducible. If it is not reducible. Can be decomposed onto this union. Now the algebraic characterization of irreducible varieties claim an affine variety is irreducible if it's ring of functions, structure ring. So this is a ring of polynomial functions on this variety, has no zero divisors, meaning that there exists no ax, y, and y which are non-zero, such that xy is equal to 0. This is a zero divisor. So proof. Okay, this is even only if condition. So I start with decomposition. A is A1 union with A2. So it's decomposition. As in this definition of reducibility. And we have a non-zero function, f non-zero function vanishing on A1. Say F1 is, F is non-zero function vanishing on A, so F belongs function, meaning that it is belongs to OA. It's a polynomial function which vanishes on A1. Such a function exists because A1 is algebraic and A is algebraic, and they are distinct. So there are some functions which vanish on A1 and don't vanish on A. And then we have G with a function in OA which vanishes on A2 by the same reason it exists. Then since A is union of A1 and A2, Fg is equal 0 on A. Then F and G are zero divisors. Okay, conversely, suppose we have Fg equals 0. So as you see, I don't prove that A is irreducible if and only if there are no zero divisors. I prove that A is irreducible if and only if there are zero divisors. It's equivalent. So you have Fg is equal 0. You take A, and these are non-trivial, non-zero functions. We define A1 is zero set of F, and A2 zero set of G. Well, intersected with A, of course. So it's zero set inside A. There are two sets, and their union is A because Fg is equal 0. So for each point in A, either F and G or G are 0. And this means that the union of these two sets is the whole A. But since F is non-zero and G is non-zero, none of these sets is contained in another. So there are two distinct sets. We don't have F belong to A, A1 belongs to A2, and A2 belongs to A1. It is impossible because F and G are non-zero. This means that if there are zero divisors, the space is not irreducible, and if it is not irreducible, there are zero divisors. Okay. What I'm telling you now, by the way, it's a paper of Emanuel Lasker, who was a chess player, but also a mathematician. He was a student of Hilbert. And so I'm going to tell you about Noetherian rings, but he was mostly responsible for this notion, and then he dropped from math, and the main glory, of course, was due to Emmy Noether, who did lots more, and he just started it, but he already had this notion and this particular theorem, which I'm going to tell you. It's called, now it's called Lasker-Noether theorem. Okay, so let me start with the definition. So there are several equivalent definitions of Noetherian rings, and I would give the most basic. So definition, suppose R is a ring, and I0 inside I1, oops, sorry, the opposite. No, sorry, write that. I3, I1, I2 is a chain of ideals. And then K terminates. That is, you can't have increasing chain of ideals which goes indefinitely. Only finitely, there could be possibly finitely many ideals which are increasing. The converse, the opposite chain, the descending chain condition doesn't work typically. So, for instance, so example, it's like a counterexample where you cannot take the opposite condition. You take ideal T, which contains ideal T squared, and this contains ideal T third, and so on. This is a descending chain of ideals, or are not equal, in, say, polynomials of one variable. But if you try to take increasing chain of conditions, this won't work. This is, you can check it right now as a good exercise. Another exercise, check Noetherian condition for Z. And still it's sort of not obvious how to construct a non-Noetherian ring, because 90% rings you can deal with are Noetherian. In particular, polynomial rings are Noetherian. As you will see today, finitely generated rings are Noetherian, and so on. So Hilbert basis theorem claims precisely that finitely generated rings are Noetherian. I will prove it in the end. All finitely generated ring. This is from the same paper of Hilbert, which was, which I showed you, mentioned last lecture. It's a paper from, I think, 1886 maybe, or 83. So it precedes both Lasker and Noether. But Hilbert did it only for polynomial and not for more general rings, and he never realized that this condition makes sense in itself. Okay, I will use this condition to describe the reducible decomposition, to show that reducible decomposition exists. So first, let me define you. So the intuition is that every algebraic variety is a union of its composition which are irreducible, finitely many. Like with the cross, with the union of a line and something curved, two curved things, whatever. So definition, an irreducible component of algebraic variety A is an irreducible algebraic subvariety, subset, irreducible algebraic subset, A prime inside A, such that A is a union of A prime and A double prime, and of course A doesn't belong to A prime. So this is strictly smaller. Well, sorry, the last condition is sort of yes, it should be A prime doesn't belong to A double prime, of course. Otherwise, you could consider like a line inside C2, and this would be bad condition. Okay. So I would immediately apply Hilbert basis theorem to irreducible decomposition, obtaining the following remark. Suppose I have a descending chain of algebraic subsets. So you have A1 contains A2 and not equal, contains A3 and so on. So if you have a subvariety which is strictly contained in another subvariety, the corresponding ideals are also strictly contained. Then you have an ideal of A1. So A1 is the biggest of them, so the ideal is the smallest. It's strictly contained inside annihilator of A2, which is strictly contained in annihilator of A3, and so on. And by Hilbert's basis theorem, we know that this chain terminates. So then the chain of subvarieties terminates. So typically what you can geometrically expect is that you have something three-dimensional, say C3. Inside C3 you have something like two-dimensional, maybe two-dimensional plus one-dimensional. And inside that you have something which is even smaller. Or you can have a union of two lines which contains a line, and the line contains a point. This is the kind of scenarios which might occur, but they all terminate because you either drop a irreducible component or you drop dimension. This is just geometric intuition. I'm not telling any theorem in that, but now I will tell a theorem that every algebraic variety is a union of its irreducible components, which are finitely many. There is a geometric counterpart of this theorem, which is Lasker-Noether primary decomposition. I will tell next lecture about that a little bit. But for most purposes, the geometric definition, the geometric theorem and geometric intuition is much better. So suppose we have A is algebraic variety. Then A is a union its irreducible components. And there are finitely many. Okay, so what we immediately obtain that cannot be infinitely many. You can't have, since we don't have descending chains, this puts already strong restrictions on the possible decomposition we might have. This is the main idea. So now let me give you the proof. So step one. Existence of irreducible components. So each point belongs to an irreducible component, maybe to two irreducible components. Like you can consider this cross. There are points which belong to only to one irreducible component. There are points which belong to two, which are intersections. So every point belongs to an irreducible component. Otherwise, you would have a decomposition. Suppose that there are no irreducible components. You would have you can decompose A would contain A1 union with A2, both containing your points. I mean, this is well, one of them definitely contains the point because otherwise we could yeah. If it's irreducible, it's already decomposed. So this contains A1 union with A2 union with, well, A1 prime, U2 prime, A3 prime, and so on. So this means that you have you split your variety onto algebraic sets, which in turn split into smaller algebraic sets and smaller. And this can be done indefinitely unless you end up with an irreducible component. But then this cannot happen because any descending chain of subvarieties terminates. So this splitting of a variety onto smaller subvarieties has to terminate, and this means that every point is contained in a subvariety which doesn't split further. Otherwise, you could split it and split it and split it and obtain a descending chain, which is impossible. Okay. So we proved the existence of irreducible components. It remains only to show that there are finitely many. So you can't have a variety which can have, like, you have one line and then you have infinitely many lines passing through it. This you don't have an obvious descending chain here because you can't split each component. It's still a union of irreducible components, but there are infinitely many, so we want to prove it is impossible. So now I have here we just proved that there exists step 2. Irreducible decomposition exists. And step 3, the number of irreducible components is finite. Okay, suppose it is not finite.
Yes, that each point itself is an irreducible component.
No, because point cannot be an irreducible component because component is something which is a variety which doesn't belong to other varieties. So each component AI doesn't belong to the union of the rest. This is the definition of a irreducible component. Yeah, and the point belongs to always belong to the rest of the components. Yeah, thank you. Okay, so I'm going to prove that the number of irreducible components is finite. Suppose it's not. Let's number them. You have, suppose, by absurd. Suppose that A is a union of AI, infinitely many, and I define BI. BI is A without AI, and then I take what is called Zariski closure. Let me define. It's a bit like usual topological closure, but Zariski closure. Zariski closure of a set F is intersection of all algebraic subsets containing F. The reason why it is called Zariski closure is because there exists Zariski topology. I will tell more about it definitely. Zariski topology is topology where closed sets are algebraic sets. And as usual, when you want to define a closure in topology, you take intersection of all closed set containing your given set. This is closure. So this is why it's called Zariski closure. Okay, and I claim that Zariski closure of BI, so BI, this Zariski closure doesn't contain AI. This is because otherwise A would be AI would belong to the union of the rest. So if so look, you suppose you have this AI. There exists a function which vanishes on AI, it doesn't vanish on the rest of, well, this is so the intersection of all the yeah, this AI does not belong to BI because AI, well, it is an irreducible subset which well, AI union with something, Hj is A. It's an irreducible component. It's a component which is reducible, and then this already contains Bi. Well, intersection of algebraic sets is algebraic because it's defined by the ideal generated by union of ideals. It's almost a tautology. So AI, well, I'm lost because it's almost trivial.
Here you wrote that AI
Does not.
doesn't.
Thanks. Yeah. Okay. So this means that, yeah, just because it's a irreducible subvariety, then the complement this means that you have a function which vanishes on AI and doesn't vanish on the rest. There is a function which vanishes on the rest and doesn't vanish on AI, and then the rest, the second function vanishes on Bi. So this is why Bi doesn't contain AI. Okay, now we have the descending condition we need. So you have a B1 contains B1 intersected with B2, contains B1 intersected with B2 intersected with B3, and so on. It's a strict embeddings because each complement is so B. There are since AI doesn't belong to the union of the rest of AJ, J not equal to I. This is by definition of reducible component. This means that for each, say A K, there is a point which doesn't belong to B to A1, A2, and so on. This is why it is strict. So on each step, you can take a point in A, say A3, for instance, on that step, which doesn't belong to the rest. So this is, which doesn't, so you take a point in, here you take a point in A3, which belongs here but doesn't belong there. And this point ensures that this embedding is strict. And this point exists because of this condition. Okay, so you obtain a strict embedding of algebraic sets, which is strict chain, which has to terminate, and this means that your set of the number of your irreducible component is finite.
I don't really get it.
Okay, you can also look at the under the following angle, that you have AI, you have a point A in AI, which A doesn't belong to the union of all the AJ with J not equal to I. There exists such a point for each this, but because this is an irreducible components. Then first, this immediately implies that the closure of the rest, algebraic closure of the of this doesn't contain this point, because this is algebraic set. This decomposition of algebraic sets AI is one algebraic set, the union of the rest is another, and this is a strict decomposition because you have a point which doesn't belong to the rest. Okay. So now we want to look at this chain. So this is A. So this is actually A contained there. This. So choose a point A small k, which belongs to A k without the rest. So this contains all of them. So this contains all AK. This contains all AK not equal to A1, except A1, because A1 is removed from B1. This contains all except A1, A2. This contains all except A1, A2, A3, and so on. This is why this chain is strict, and they're algebraic because by definition, intersection of algebraic subvarieties is algebraic, because algebraic subvariety is one which is given by equations, and if you have intersection of subvarieties, this is something which is given by sets of equations for all the subvarieties. This is why this Zariski closure is algebraic. This is why all the sets are algebraic, so I obtain a strict chain descending algebraic sets. Okay. Now we can proceed to the proof of Hilbert basis theorem about Noetherianity of polynomial ring. Well, finally generated ring, but if you think of it, this is enough to prove just for polynomials. This is the main idea of the argument. But yeah, so for this theorem, Hilbert basis theorem immediately implies that there exists a reducible decomposition for each affine variety. I said manifold, I meant variety, sorry. Yeah, because sorry, Mark. If a Hilbert basis, so if C of T1 dot Tn is Noetherian, then all finitely generated rings are Noetherian because, okay, you have a polynomial ring and you have a quotient ring R. Then here you have a chain of ideals, ascending chain of ideals. I1 go inside I2, inside I3, and so on. Then you can take preimages of these ideals. So this is pi. You take pi minus 1 of I1. It would be strictly embedded to pi minus 1 of I2 because the preimage of an ideal is an ideal, and this is surjective. Pi minus 1 of I3, and so on. So if you have an increasing chain of ideals in R, you would have an increasing chain of ideals in polynomial ring, which is impossible. So this also proves the following corollary. So suppose you have a surjective map of homomorphism of ring. Surjective homomorphism of rings. And suppose that R1 is Noetherian, then R2 is also Noetherian. Okay. Yeah, and this implies in particular that you would have a irreducible decomposition for each finitely generated ring for each for algebraic varieties in particular. Okay. Now, to prove Hilbert-Bayes' theorem, we just need to prove that a Noetherianity for polynomial rings. And there's another trivial remark, is that to prove that remark, to prove that polynomial ring is Noetherian, it suffices to show that R of t, the polynomial of one variable, is Noetherian for all Noetherian rings R. Then can use induction. The base field is clearly Noetherian. There is no ideals. And then you just add t one by one. And so you have C Noetherian. By this implication implies that C of t is Noetherian. This implies then C, I say T1 of T, T1, T2 is Noetherian, and so on. So to prove Hilbert-Bayes' theorem, it suffices to show it for just a ring of polynomials of one variable. This is a portrait of Emmy Noether. So she did it, she axiomatized the whole thing, and in fact she was extremely important because before nobody quite understand what goes on. There were some examples, like Hilbert did it for polynomials, Lasker did it for converging, for germs of analytic functions, but there was no axioms. And she found axioms, and then it simplified the method incredibly. And this is Lasker. He was, of course, much more famous as a chess master. This is why he had his own stamp in Deutsche Demokratische Republik, the West East Germany. And yeah, he was, I think, the longest chess champion in the world. So he was a champion for 27 years or something, and this is the biggest time anybody was a chess champion. But before that, he was a student of Hilbert, and he did lots of very nice mathematics. Unfortunately, he stopped and became a chess master. Okay. I'm going to slightly reformulate the Hilbert-Bayes theorem.
Here it was just an example. We haven't proved.
No, it was implication. If we can prove that, we're done. But of course, we didn't prove it yet. So there are two approaches to Noetherianity, and the one which is due to Noether is much more powerful. When you just do essentially axiomatic things. So definition. But this definition is implicit in Hilbert, of course. An ideal I in R is finally generated if there exist generators, there exist A1 dot AN inside this ideal such that I is equal to what is denoted by I1 dot AN in parentheses, and this means that all sums of form sum of BI AI, where BI has coefficients inside our ring. This is standard notation for ideal generated by things. Sometimes you use angle brackets, or you can use round brackets. I think here I use angle brackets. Okay. Now, yeah, let me give you an example. So, example. Well, it's sort of easy to find examples of ideals which are finitely generated because most ideals are finitely generated. For instance, in Z, all ideals have form N. I mean, Z is principal ideal ring, so all ideals are generated just by one element. And another example is, so it's finitely generated. And example of something which is not finitely generated, you take smooth functions on a line. And as an ideal, you can take an ideal all functions with vanishing derivatives f, which are smooth, such that f any number of primes, any number of derivatives in 0 equals 0. No, it's a good exercise to prove that it is not finitely generated. It's not extremely hard. The idea is that, okay, you have something finitely generated, then you find a function which goes to 0 even faster than all the functions which you use as generators, which goes to 0 as you go to 0, like the limit, the asymptotics, the limit goes to 0 faster. And this gives you an example of, well, this proves that this ideal is not finitely generated. But generally, it's hard to find ideals which are not finitely generated. Even this is not obvious. And more general, well, so Noetherianity is very common property. If you see a ring, you expect it to be Noetherian, and then probably is. Okay. Sorry?
The ring is an infinite number of generators, the polynomial ring.
Yeah, but I doubt you can find this kind of ideal even in that ring. Well, yeah, it's not Noetherian, so you should. But it's still not obvious how to find it. Okay, maybe you need to take an ideal which like vanishes on each variable faster and faster, something like that. Okay, so now lemma. Suppose that I0 goes inside I 1 inside and so on, inside I n inside and so on, is a chain of ideals. And I is equal to union of all them. And suppose that I is finally generated. Then this chain stabilizes or terminates. So it's a finite chain. And the proof is quite obvious. So you have A1 dot AN is the generators. And they belong to I, belong to IN for n sufficiently big, because each of them belongs to some of this I, so the set of all these generators belong to the biggest, the ideal with the biggest number of them all. And this then, but this set of generators generate I. So this means that I is equal to IN. Okay, this was the argument relating finite generatedness and Noetherianness, which is pretty much the same if you do it with some care. Okay, so the first claim, which is almost straightforward and obvious, that if you have a ring which is with all ideals finally generated, it is Noetherian. R is Noetherian if and only if in R are finitely generated. Okay, one direction of this result is clear from this claim, from the previous lemma. So if all ideals are finitely generated, then chains stabilize. Okay, you have a chain of ideals, you just take their union, the union is finitely generated, and you apply this lemma. Conversely, if all chains stabilize, then ideals are finitely generated. Indeed, you take ideal I, you take its subset generated by A1. And then you take its bigger, possibly bigger subset generated by A1, A2. And if I is not generated by A1, you can always find A2, which is in complement to, it belongs to I, but doesn't belong to A1, so the ideal generated by A1, so this inclusion is strict. Now, this ideal generated by A1, A2, if it's I were done, it's finitely generated. If it's not, you can have A3, which doesn't belong to this subset, but belongs to I. So you have A1, A2, A3 strictly embedded, and A1, A2 is strictly embedded there. And you can go on and on. Unless this chain stabilizes. If it stabilizes, this means that you found a set of generators for I. If it doesn't, well, then you have a non-stabilizing chain, which is impossible by that assumption. So if all chains stabilize, the ideals are finitely generated. Okay, so this was actually the original version of, well, this was what Hilbert proved. He didn't, he was not that interested in chains of ideals, but in existence of a basis of generators. Hilbert basis theorem is precisely existence of generators of an ideal. Okay. To the most powerful, why this idea of Noether is that powerful is because you can apply Noetherianity even to models. So definition, R model is over a ring, is a group or a vector space. Well, when I speak of vector space, I mean that we always consider rings over a field. Otherwise, it would have been a group if it's Z model, for instance, or abelian group. Depends on whether your ring is over a field or just by itself, like Z, for instance, like integers, equipped with an algebra homomorphism. R goes to endomorphisms of M. This is one of the possible definitions, but the idea is that models over a ring is the same as vector spaces over a field. This is just you can add vectors and you can multiply them by coefficients which belong to your ring. Okay, example. So R is R model. By trivial reasons, you have R1, R2 goes to R1, R2. This is your multiplication by elements of a ring. Now I subset R is R submodel if and only if I is an ideal. This because to be ideal, you have to be, if you want I to be ideal, you want to be able to multiply I by elements in R, and this is precisely the same as for submodels. Submodels are things which are closed under multiplication by R. Okay, now definition. This is generalization of the definition of ideal, I mean of a Noetherian ring, or M is Noetherian R model if any ascending chain of submodels, you have M0 inside M1, inside and so on, inside Mn, and everything in M. We wanted to stabilize or terminate. This is precisely the same condition as for ideals. And since ideals are the same as submodels, it's just generalization. Okay, and the trivial remark is that this condition behaves very well with respect to submodels and quotient models. So remark, a submodel, which means that it is a subgroup which is preserved by this endomorphisms which come from R. So it's preserved by multiplication in R. A submodel and a quotient model. quotient model is again a quotient space which by a subspace which is preserved by R, so the quotient is also preserved by R. R of a Noetherian model. M are as well Noetherian. Well, so proof. If you have M goes to M1, for instance, surjectively, and you have a chain submodels here, you can just take a pre-image of this chain of submodels. So M, like 2M prime, and it will be M1, inside M2, inside and so on. You take pre-image, it's surjective, so the pre-image will be a strict sequence, which is impossible because because in M is Noetherian. And conversely, if you, not conversely, but if you have a submodel in N in M, and you have a chain submodels here, this chain submodels is a chain submodel in M, so it has to terminate. Okay. And the main idea how one proves Noetherianity is just using these quotients and the submodels and doing essentially working with models instead of rings and ideals. Yeah, and of course, finally generated model is just a quotient of a free model. So definition, Rn is a freer model. It's just direct sum of several copies of R, and M is finally generated if M is a quotient of Rn. There's a certain confusion which will have lots of problem in the future, because finitely generated ring is not finitely generated as a model. It's not a quotient of, it's infinitely, its dimension is infinite. And you see finitely generated models have finite dimension over, they have finite rank, so to say. They're a quotient of finite direct sums of your ring R with itself. Okay. Yeah, and now a statement which is very similar to what we already had, is that M is Noetherian. So our model M is Noetherian if and only if all its submodels are finitely generated. This is well already had it for ideals, and the proof is literally the same. So you have it already. Yeah, I leave it as an exercise. Yeah. Now, in another observation, which is also trivial, is R is Noetherian if and only if R is Noetherian is a Noetherian model over itself. To see that, you just notice that submodels of R as our model are ideals. So the chains of ideals are the same as chains of submodels. Something we already discussed. Okay, there is another observation which is more or less trivial. It follows from what we had already discussed, is that if you have a ring and a smaller ring, if you have a ring R1 inside R2, and you have R2 model M, and suppose it is, we can consider it as a Riemann model. If M is Noetherian as R1 model, then M is Noetherian as R2 model. So if it's, say, finally generated as R1 model with all submodels, these submodels are also R2 submodels, so they all chains also terminate. Another observation, which was on slides and I didn't give it, is that if R is Noetherian, so R is Noetherian, then R power n is also Noetherian. It's just by coordinates. You just check coordinate by coordinate that if you have a chain, then it increases in all, it should stabilize in all coordinates, so it really stabilizes. And there is something I would use at some point, that, for instance, if you have R of t quotient by Tn is Noetherian, if R is Noetherian. Of course, we want it for R of t, but at least we have small part. If for quotient, because this is Rn. And Rn is a Noetherian model. If it's not, it's even Noetherian over R, so it's definitely Noetherian over RT. Okay. So now I'm almost ready to start the proof. Sorry? Yeah, and you have R2 model. You consider it as R1 model. And if it is, if it is Noetherian as R1 model for smaller ring, it's Noetherian for the bigger ring. Because every chain over bigger ring, or chain of submodels over a bigger ring, will also be a chain of submodels over a smaller ring. This is why it would stabilize always. If it's Noetherian as R1 model, this means that it will stabilize as sequence of models over R1, but then over R2 is also will stabilize. Okay. Now I'm going to start the proof. It's almost done, in fact. There's a proposition which is related to long division of polynomials. It's almost you can say, okay, let's divide polynomials, but in fact it's slightly easier to avoid long division and just to state it as it is. I will use it in the next slide. So proposition 1. Suppose you have an I is an ideal in R of t. Ideal. And then we are written, or J, it's J. When we are written J0, it's an ideal in R. Ideal generated by leading terms. Leading means the terms of biggest coefficients of biggest degree. Terms, well, coefficients of leading terms of all polynomials P of t inside J. So this means that if you have a P of t is equal to a n t power n plus a n minus 1 t power n minus 1 plus and so on, you take a n, it's a leading term, and you generate the ideal by all these coefficients. It's an ideal in R. Okay. By leading terms of, let's not all of P, but of subset of Q1 dot Qn of J, but then by finitely many polynomials, but then I suppose that J0 contains all leading terms. This is the same. I mean, you can start with what is important that this is finitely generated. Of course, you are going to prove something about R of t, where R is Noetherian. So every ideal, we can expect that every ideal over R is finitely generated, and this is what we do. I also assume that all Q has the same degree. So degree of Qi of t is k. And then for each polynomial p of t in this ideal J, there exists p1 of t, which also belongs to J, but very small degree, is less than k, such that P1 minus P belongs to JQ. This is the ideal generated by Qi. Let me draw a picture. So you have R of t. Inside you have two ideals, J, and then JQ. J is, we don't know if it is finitely generated, but JQ definitely is. Want them to be equal, but yet we are not going to prove that yet. And then you have ideal leading terms. J0 belongs to R. And this is leading terms of these guys as well. Okay, so the first observation, it's so suppose that you have P of t has the same leading term as Q of t. Same leading terms. But Q degree Q of t is equal k, and degree P of t is n bigger than k. Then, obviously, P of t minus t power n minus k Q of t, the degree of this element is less than n. This is trivial observation. You just can, this is like division. You can subtract, they have the same leading term, so the difference has smaller degree. Okay. So this would be the basic observation. So step 2. We take leading term a n, a leading term coefficient of p, and we can take q, k polynomial of degree k. Q is a sum of ui of t. Ui are elements in our ring R, such that leading term of Q is the same, is n. Then the degree of P minus Q is less than degree P. And also, P is equal to this, let's call this polynomial P1. P is equal to P1. Do we already have P1 here? No, we already have P1. Let's call it P prime. Oh, P tilde. P minus P tilde belongs to JQ, because this is Q, and Q is a linear combination of Qi which belong to Q. Yeah, so okay. So I found a polynomial of smaller degree which has the same properties, and then I can use induction by degree. Using induction by degree, we find another polynomial which is again belongs to the same. It's equal to P modulo JQ, but then it has smaller degree, and smaller degree, and smaller degree. And every step we subtract the leading term, because we know that the leading terms can be expressed as leading terms of Qi. In the end, we obtain something which has degree less than k, because all these polynomials have degree k. Make clear so far? Okay, now we can prove Hilbert's basis theorem. So as I told you, it would immediately follow if we prove that neutrality of R implies neutrality of R of T. This is what I'm going to prove. So proposition: if R is Noetherian, then R of T is Noetherian. Okay, so the first step we take an ideal I inside R of T. We need to prove that this ideal is finitely generated, because finitely generated full ideals are the same as Noetherianity. And then take Ji0. It's an ideal in R, ideal generated by leading terms. Terms of P of T inside Ji. Okay. This is R is Noetherian, so this ideal is finitely generated. And we can find Q1 dot Qn polynomials inside I, such that leading terms of qi of t generate I0. And then we can always take the polynomial, the biggest degree polynomial of them all, and multiply the rest by t appropriate power, so that they have the same degree. This can be always assumed. So degree of qi of t is equal to k. This is what we need to apply the proposition 1. So by step 2, we apply proposition 1, which implies that all for each p of t inside I, there exists q of t generated by qi, such that p of t minus q of t has degree smaller than k. Let's denote JQ, the ideal IQ, the ideal generated by Q. By QI. Okay. So this implies the following existence of the following surjective map. We can take intersection of I with the so I belongs to R of t, and then R of t is a graded ring, I mean a graded space. It's generated by consider monomials as generators of RRT over R. So I take intersection with the subspace generated by monomials 1, t, t squared, and so on up to t power k minus 1. This is a free, so this belongs to, this is a R submodel in R of t. And this is surjectively mapped to I quotient by IQ by this argument. Because every polynomial in I up to IQ comes from a polynomial of degree k minus 1. So the natural map from this to there is surjective. Is it clear? Again, so we know that every element of I up to elements of IQ has degree less than k. So consider this, let's call this P1, and consider P1 as an element in this intersection. It belongs to I, so it belongs to this intersection, and it has degree less than k. This is just polynomials of degree less than k, which belong to I. And this polynomial represents this P of t up to Q of t, And Q, so this belongs to, if you consider this as element of a quotient, I by I of Q, this is precisely P1. This is why it is surjective. Okay. But this is already, so this is a submodule, this intersection, intersected with the subspace generated by 1, t squared, and so on, n minus, k minus 1. This is r power k. This is intersection, so this is a submodule of a Noetherian model of r power k. This is Noetherian over as R model. And every Noetherian model has is finally generated. Then it is finally generated. And denote its generators by, I think it was ui here, u1 dot dot um. Um of t is generators of I over IQ. They are generators over R, but then they are generators over R of t as well. So what we obtain in the end is that I is generated by this set of generators of two types. So I, step 4, I is generated by Q1 of t dot Q n of t, and then P1 of U1 of t dot U m of t. Indeed, Ui generate I quotient by IQ over R, and then over RT, of course. And Qi generate IQ over R of t. So together, this set of generators is a finite set of generators for I. This finishes the proof of Hilbert-Beige's theorem. So the story goes as follows. So there was a huge activity in 1870s, 1880s. Max Noether, the father of Emmy Noether, was one of the principal actors, as well as Clepsch and Gordon. People were writing a set of invariants, generators for invariants of group action on some vector spaces, like tensor invariants, invariants in symmetric spaces, and so on. Mostly in symmetric powers, like polynomial invariants. And it was a whole lots of work in that, because these papers with all this list of invariants took 200 pages, because the list of invariants or polynomials they were writing took most of the papers. And then Hilbert proved that there's no reason to write these invariants, because the basis always exists. And he even wrote an algorithm, which I told you about, how to find this basis. This was extremely disappointing for Noether and for Max Noether and Gordon, because they so killed the whole part of math. But in the end, it was useful, because in 1960s, Mumford resurrected this Hilbert's approach, resurrected the invariant theory, and built what is called now geometric invariant theory, which is based essentially on both ways of thinking about invariants, on Hilbert's and on Gordon, Noether, and Clebsch. Okay, but existence of a basis was for Hilbert the main application, and not Hilbert-Nurstein, that which was proven in the same paper. But of course, now people care more about both, but more about Hilbert-Nurstein. Okay. And of course, for us, it's foundational because when you do commutative algebra, you always assume that the rings are Noetherian. There are people who do non-Noetherian rings, but they're minority, and it is really special and very complicated business. Okay, before I finish, let me tell you a bit more about geometric applications. So the idea is that if you have a smooth manifold, it's always smooth. Algebraic set, it's always irreducible, and typically you deal with smooth things. So singularities are usually exception. Not always, but the typical object you find in geometry is a smooth manifold. So definition, an algebraic set, a set A, so a point X in an algebraic set A is smooth, and the same algebraic set is smooth in X if there exists a neighborhood of A U. So it's a neighborhood in A, which is smoothly diffeomorphic to a ball, to Rn. So this means that intersection is a smooth submanifold. It turns out that you can determine a smooth point by using algebraic approach, using commutative algebra. There is a criterion which I'm not sure I will have a time to tell in the end of this lecture because it's really advanced, but maybe I will. Also, the diffeomorphism can be chosen polynomial. Remark, this diffeomorphism can be chosen polynomial. Well, this is done by application of inverse function theorem. So if you have a smooth point of k-dimensional manifold, to build a diffeomorphism, you need to find a map which is isomorphic and differential. So you can just take coordinate functions on any other set of functions which give you this isomorphism. In particular, you can choose them polynomial. You can, in fact, choose them coordinate, which is slightly better, even better than polynomial. And if you have a map which is isomorphism on tangent space to a point, then it is diffeomorphism in a neighborhood by inverse function theory. Okay. So what I could tell you, in fact, was that you have a map to Cn, but this, unfortunately, this is not that much true. What is true is that your map are complex analytic maps to a ball. So you have phi from this neighborhood U inside A to a ball in Cn, and it is complex analytic in the sense of having Taylor decomposition. Taylor decomposition is not immediate from the from the inverse function theorem, but on the other hand, it's immediate from Cauchy formula. You just check that your map is not only differentiable, but complex differentiable. This is because you have complex structure on everything, and your map is complex valued polynomial. And then you apply Cauchy formula to have a Taylor power series for all functions you can get. All complex differentiable functions are analytic. They have a Taylor series. So regular functions are complex analytic. That is have Taylor series. In U. This is again geometric approach to algebraic geometry. It has very non-algebraic. In fact, it would make no sense for other fields such as p-adics or even well, for most other fields. However, what is good is irreducibility would follow from for free from smoothness. So this one more reason to restrict yourself to irreducible subvarieties, because smooth things are reducible. So claim let A be a algebraic variety which is connected and smooth. Then A is irreducible. And by connected, I mean connected in the usual topology. In fact, if you are interested in the Zariski topology, the connectedness in the Zariski topology implies the usual connectedness, and this is extremely hard. So it takes very advanced complex analysis, complex analytic arguments. Okay, so the proof is sort of easy. So you need analytic continuation principle. So what we know is that if it is reducible, you would have two regular functions which are multiplied to 0. So you would have reducibility of A is equivalent to having 0 divisors. Or A has 0 divisors. It turns out that analytic functions have no Z divisors. This would immediately imply, of course, we know that regular functions are analytic, complex analytic, and we know that complex analytic, if we know that complex analytic functions have no 0 divisors, we are done with the irreducibility of smooth algebraic varieties. Okay. So let's see why complex analytic functions have no 0 divisors. So the first is that if you have Taylor series, so F with G, complex analytic, you can take product of the Taylor series of non-zero Taylor series is non-zero because, well, if you are, you can replace the Taylor series, embed Taylor series into formal, and consider the ring of formal powers. It's like infinite ring of infinite series without any condition of convergence. This has no zero divisors. Okay, why it has no zero divisors? You can take, if you have two elements in this ring, you can multiply these two elements, but then you can take the graded component. There are infinitely many graded components, of course, because it's a series. But you can, if the smallest degree ones are non-zero, then the rest is non-zero, and the smallest degree are polynomials. You just multiply polynomials, you obtain that this ring has no zero divisors. And then your Taylor series are embedded to that. This implies that if fg is equal 0, then Taylor series for f or g is equal vanishes. And another is analytic continuation principle, which says that if, so analytic continuation, if f analytic function and f is equal, well, a Taylor series for f vanish at some point, they vanish everywhere. This, since, of course, everywhere on connected components, but since your variety manifold is connected, this finishes the proof. So why they vanish everywhere? Okay, look, you have your function. It has Taylor expansion 0 at one point. This means that it is 0 in its neighborhood because analytic function is equal to its Taylor series. Okay, consider, so the set where it is 0 is open. On the other hand, it is closed because the limit of, if it's 0 in the limit. So it's an open and closed set. It has to be everything because our manifold is connected. So this is why we cannot have zero divisors for complex analytic functions. Yeah. So this is the argument which I just gave. Okay. Yeah. Thank you very much. I'm done. So next time I would